So we want to focus on energy storage. We need to essentially significantly reduce our CO2. We need to do so in the coming decade. 80% of CO2 emissions come from tailpipe. So if we can make them electric, we can significantly reduce the CO2 emission come from light-duty vehicles. So lithium-ion batteries cost has reduced by 10 times over the past decade, and it has a worldwide mass production. So the question is, how can we accelerate the translation and go through essentially many value of death as going from TRL level, fundamental research, to translation. The technology scaling up can be also limited by availability of materials. Right? So that's a challenge we face, how we think about more collaboration as various countries has introduced essentially policies to accelerate domestic production. So with that, I just want to conclude it's really important to consider time, or shorten the time, how to really lower the cost, and how to increase scale, and then largely how to train and mentor future engineers and scientists and entrepreneurs.
Energy is broader than just the chemistry and the electrochemistry. Regulation, engineering, networks are also very important. And the idea is to unite all the powers in Israel, all the forces in Israel, to work changing the energy economy of the country, and to meet the challenges that is well dictated by the climate crisis. We have four needs. We have portable devices, mobility, and we have the great challenge of large energy storage. The chemistry is the most important issue, what we put in the cell in order to reach an energy content. The best composition for electromobility, the so-called nickel-rich NCM cathode materials. So all of these curves demonstrate the improvement that can be reached by doping. These materials, the nickel materials, are the best for electromobility. Rechargeable lithium metal batteries are the best of the best in terms of energy density, but we want to have a situation where we can control the surface in a way that we have surface that accommodate the morphological changes. It appears that if we use fluorinated solvent, this structure allow unique surface chemistry on the surface, because the fluorine, the best system for large energy storage, if we would have enough lithium, is the combination of graphite and LFP. But because we don't have enough lithium, we have to go to sodium-ion battery technology, and here we have a very nice follow-up. We cannot use graphite, but we can use carbon materials. So this is the best technology that we can offer for large energy storage if we deal with electrochemical power sources.
I would show something about the markets, manufacturing, the battery system technology issues. If we find applications where we can use electricity and batteries directly, because there will so much need for the hydrogen in other fields. The forecast for the battery demand in the global markets is here in the Bloomberg forecast, which is roughly somehow in the middle of the different ones. If you look to the priorities in the battery development from the automotive manufacturer's point of view, it's cost reduction and fast charging. It's not the technology itself which really makes a change, it's the price at which we can offer this into the market. Regarding manufacturing, the ministries have financed in the last year several pilot lines for battery cell production, and this is for manufacturing elements along the whole value chain. One more word about recycling. There are strong targets with regard to recycling. So, and finally, and this is mainly the things I'm working on also, when having cells of any type, every shape, whatever, there are a huge number of aspects which have to be looked at for the integration in the system. The main problem is really what was discussed this morning, long-term storage. We can do balancing for 24 hours, relatively easy, but we can't do for 3 weeks. And this is where we have to go additionally with hydrogen or something else.